Okay, welcome to class. Welcome to class. Okay, happy Friday. We will pick up right where we left off last time. So let me first talk about the objectives, and then we're going to try and make sense of the bizarre demo we saw at the end of class last time. Then we'll do a reading quiz right after that. So first up, our learning objectives for today are we're going to explore what variables actually influence what phases are present. We'll do that in a unary phase diagram and eventually a binary. We'll use something called Gibbs phase rule to predict something called the degrees of freedom, or things we can change that won't mess with our system's phase equilibria. We'll be able to sketch how free energy changes with temperature and pressure when you account for different phases like solids, liquids, and vapors. We'll identify things like solidus and liquidus lines, which help us know what are the limits of solubility within your different phases. And at the end, we'll get into something called Vegards law, which helps us predict solubility limits, right? So maybe to begin with, actually, let's do the reading quiz first. We've got 3 quick questions for reading, so grab your clickers. Let me make this bigger. The first question says, in this phase diagram, if you identify region 1, it wants to know what are the phases present in region 1, A, B, C, or D. Okay, get your answers in for what is region 1? Okay, we're going to wrap it up in just 10 or 20 seconds. Get your answers in. What is region 1? Okay, we're going to end it. What is region 1? Okay, most people realize it's alpha and beta. Let's do the next one. What is region 2? What is region 2? Okay, another 10 seconds. This should be straightforward. Okay, I'm going to end it. Definitely beta and liquid. And then the last question is, what is region 3? And it's technically not a region, it's a point, if that makes your answer any easier. Okay, get your answers in. The last reading quiz question. Okay, I'm going to wrap it up. What is region 3? Definitely a eutectic point. Okay. Okay, let's dive into chapter 10 then. Chapter 10 is all about phases, right? Phases of matter. So let me just ask, what are we talking about when we say phases of matter? Can I get some examples? Shout something out. Solid, that's a phase. What else? Liquid, gas. Is that it? Critical, supercritical liquid. Someone will say plasma. Bose-Einstein condensate. Is that it? Those 5, 6 things, is that it? Is that all the phases that are out there? I'm hearing yes and no's. Like, raise your hand for yes. Raise your hand for no. Okay, there's clearly more, then why can't we name them? What else are we talking about? Let me pick on Josh. Ah, good question. So you're asking, when we have like in that phase diagram, which was alpha plus liquid, does that represent its own phase? No, that's a multi-phase. That's a 2-phase mixture in that case. But are there other phases? Anybody want to hazard a guess? Well, let me answer with this. Let's talk about the iron wire demo. Last time we had this iron wire. We heated it up, and it started to get longer because most things expand when you heat them up. And so the wire started to droop. Now we kept on heating it. It wasn't until the very end that I turned that lever back down. So I was still turning it up, so it's still getting warmer, and yet you couldn't see it as easily on the heating up, but it drooped, and then it got higher a little bit, and then it kept drooping like normal. And then when I killed the power, it was really easy to see it. It went up, and then it dropped down for a minute, and then it went all the way back up to where it started, right? So how do we explain that in terms of phases? Anyone want to take a stab at that? Any guesses? Yeah.
So when it drooped and it paused, we let it reach equilibrium and then start again. And then so when we go back, it wanted to go back to the equilibrium and then.
Oh, you're so close. It did reach an equilibrium, but an equilibrium between what and what? You're exactly right. When we say equilibrium, that means that there's a reaction, right? So in fact, iron at room temperature, we call it alpha iron, right? Alpha, we'll learn what alpha means in terms of how the atoms are arranged in like one more chapter, or two more chapters. But for now, just consider that it's a way of arranging atoms. Just like if I could take students, I could arrange you in like a square lattice or a hexagonal lattice or whatever. Right now, consider that as one type of lattice, and we call that alpha iron. But there is a temperature when you heat iron up where it actually switches phase. Right? The atoms, even though they're all there in that wire, they rearrange themselves to a different crystal structure. And we call that, even though they're both solids is too broad of a term for a phase. There are subsequent, like individual phases within the solid category. And in the case of iron, there's 3 different ones. As you heat it up, it goes from one phase, alpha, to the gamma phase, and then it turns into delta. Right? And I don't know who chose these letters. That's just what people know them as, right? So what we saw in that wire is we saw it transition from one arrangement to a different arrangement. Now, if you had to guess the high temperature phase, do you think it's more densely packed or more spread out? Why would you guess that? Yeah, because, no, it's wrong. It's the other way around. Other way around, Rob. Help us understand this.
Well, I'd imagine it gets denser because that's why the wire went back up.
Yeah, we were still heating this thing up, so it should have kept on getting longer, but it stopped and it went shorter, meaning all those atoms, for whatever reason, thermodynamics, right? They decided they would squeeze together a little bit closer into a different crystal structure. And then once they had all the atoms had squozen into some new different crystal structure, then it's free to expand with thermal expansion just like before. Squozen? I don't know how you say that. Right? And then we saw the inverse happen when we cooled it down. That high temperature phase, which was thermodynamically favorable, as soon as you cool below a certain temperature, the atoms say, it's about enough, and they stretch out to their more stretched out arrangement. And then they continue shrinking, just like normal, as you cool it down further, right? So the reason I like the iron wire demos, it draws attention to the fact that it's not just solid, liquid, and gas, plus vapor, plus the other things that people said, or whatever things you guys said. It's actually a whole bunch of different types of solids are out there, like a gazillion different types of solids. There's tons of them, and we're just going to learn about a few of the important ones in this class, okay? So that said, why do we care about phases as engineers? What do you guys think? Why should you care about phases as engineers? Well, just take the iron wire demo. If you're an engineer who uses iron, why would understanding phases be useful to you? Maybe turn to a neighbor and say something. No one wants to talk. Okay, what do we think? Let me pick on, I think it's John in the black shirt with the beard.
So you can determine what kind of structure will come about through these phase diagrams if it's heated fast or slow, correct?
Yeah, so you'll be able to predict, like the phase diagram, think of it like a map. It's just like a treasure map. It tells you where things are. The phase diagram tells you what phases or what structures are present as a function of what? You said as you heat it up. So as a function of temperature for one thing. Anything else? Concentration. So let's call that composition. We'll come back to that in a moment. Anything else? There's one more big one. Pressure. Right? As you change the composition, if you had like a two-phase mixture, let's say like sugar and water, you can change the composition of pure sugar all the way to pure water. the phase diagram will tell us what phases are present as you change that. As you change the temperature, it'll tell you, and as you change pressure. Now, pressure is less common to show phase diagrams as a function of pressure. They exist, they're just less common. Usually they're plotted against composition and temperature, okay? So again, why do we care about this? It tells us structure, so what? As engineers, like, do you really need to know it? How come? Anybody else? What else were you thinking when you were discussing? Any other reasons why you ought to care about this? Why you're in this class? Why some advisor said, let's make our mechanicals and civils take this, not just the material students? Is there some reason? Yeah, remember your name.
Your materials will have different properties depending on what phase they're in.
Yeah, so absolutely. In fact, there's something critical in material science. We call the tetrahedra of material science. That's the nerdiest thing you'll hear all day. Right? You ready for this? The tetrahedra of material science. So you've got structure, property, you've got processing. Actually, I can leave out the back corner. I'm just going to do the 4, not pyramid. Right? You've got processing, and then you've got a performance. Sometimes they put performance and properties together. The idea being that the study of material science is all about understanding the linkages between these 4 things, right? So for example, if you need a certain property, a certain yield strength, or a certain stiffness, right? That is going to be tied to the crystal structure. It'll not only be tied to the crystal structure, it'll be tied to what we call the microstructure, which is something, at the micron scale. And how do you achieve the different structures? Well, you have to process them in different ways, right? You have to process them in different ways. And as you process them, you can change the properties and change the performance, right? These things are all linked to each other. So the study of material science is about using things like phase diagrams and lots of other tools we have to understand these relationships. So you don't just build a car out of aluminum and say, aluminum is always aluminum. You understand that actually it depends on what type of aluminum. There's a whole bunch of different types, right? And like in terms of composition, and there's a bunch of different microstructures we can achieve, and we can make those microstructures with different processing techniques. So hot rolled versus cast versus plastic formed, right? There's all sorts of ways to make these things, and you can't change one without changing the others, is what it's really getting at. Okay, so I'm going to skip that activity. Oh no, I've done that. All right, that'll be okay. So let's talk about this one. Let's consider the simplest scenario we've got, which means just one component, pure water, right? Pure water. As I increase temperature or as I increase pressure, I can change what phase the water is present in, right? You've got solid, liquid, and gas, or we call it ice, water, and vapor, I guess, or steam, whatever you want to call it, right? So at high temperatures, what should we have? That's where you should have your gas, right? At really high pressures, what should we have? Yeah, if you squeeze it enough, you'd think that you're going to have solids, right? And then if you take a gas and you squeeze a gas, what will you get? First, you're going to get a liquid, right? So there must be a line here when if you go from increasing pressure that you'll end up with a liquid, right? Now, water is unusual. What do we know about ice and water? Does ice float? Yes. So therefore, that changes this diagram, right? If you squeeze on, basically, well, which one's more dense then? If ice floats, is it more or less dense? Less dense. Therefore, it's unusual. If you were to squeeze on ice, since it's less dense than water, you should cause it to transition to liquid. That makes sense? If you took ice, like a block of ice, and I squeeze on it, technically I should be able to push it into the liquid regime. Now, in practice, this is hard to do, and a lot of people thought this is why ice skaters could ice skate for a long time, because you've got all the weight of your body on a thin little blade, and they thought, oh, maybe it's the weight of your body pressing on that ice, turning in a thin little layer into water. They've actually debunked that. There's other reasons why ice is slippery. That was a pretty good guess. Anyways, this is our phase diagram for water, right? Phase diagram. This tells us as a function of pressure and temperature where you can find these different phases. And this is just a cheesy sketch right now, but it's still pretty useful. For example, anybody like to bake in here? Any bakers? Jeff. Oh, you heard this when we talked about it in lab. You can't answer. All right, somebody else. Matt, do you like to bake? Have you ever noticed that instructions sometimes give you 2 different times or temperatures depending on where you live? You ever notice that? It'll say if you're at a certain elevation, double your baking time or whatever. Nobody ever noticed that? Anybody notice this? Is it just me? Some people have seen this before.
Yeah, they also have it for like if you're using a metal pan or if you're using a glass pan.
Absolutely. So what's going on? Let's talk about that as it might relate to this phase diagram. How might that make sense? Let's do Anthony.
Isn't it because at higher elevations you have less air pressure on the food that you're making, and so the water molecules inside that food?
So basically, we went down in pressure at high elevation.
So they're going to remain solid for longer. So you need to
liquid.
Solid, but like,
Oh, you're really on the right track. So think about it. When you cook something, it's oftentimes, it's like, it's high. It's a higher temperature than the water would normally be boiling, right? Or you're boiling the water, maybe. Now, let me ask you this. Does the boiling point of water change as a function of pressure?
yes.
How do we know that? Because we have a line right here. This line represents the boiling point as a function of pressure, right? So if I was going to draw Salt Lake City, Utah, maybe it boils right here. How will that compare to Los Angeles? Well, Los Angeles, do we go up or down in pressure? Remember, think of the air like it's an ocean of air. That's the way I remember this. And we live high up in the ocean where there's less pressure. Down in LA, they live at the bottom of the ocean of air, right? So there's higher pressure and smog, right? So they went up in pressure from Salt Lake City, wherever we're at. They might be up here somewhere. So their boiling point is actually at a higher temperature. So their water is literally boiling at a higher temperature. So they don't have to cook it as long because it's hotter, right? It's cooking your eggs or your rice or whatever's happening at a higher temperature. So these are actually kind of useful, not just for cheesy stuff like figuring out boiling temperature stuff. They're really useful for processing materials. So let's keep going. Let's label some points on this and talk about some key points. Let me change color. All right, our first point we're going to talk about is this point where all three of those come together. We're going to call that point A. We're going to call this one right here point B. This guy over here will be point C. And then this one out here will be point D. So somebody tell me, what is point A? We call that the triple point. What does that mean by triple point? What is the name triple point? Yeah, what this means is there is a single temperature and pressure which exists for this system where gas, liquid, and solid all coexist in equilibrium, right? All these things will coexist. Now, what's happening at B? What does B correspond to? Solid and liquid. What do we call that in chemistry and science? The transition between solid and liquid, we either call it melting or freezing, right? That's the melting point, or the freezing point if you're cooling down. What about point C? What do we call that?
Evaporation or condensation.
Yeah, we call that boiling point or the condensation point?
Yeah.
I don't know if that's what they call it. Let's call it that, the condensation point. Right? What about point D? That's just a guess. We'll come back to point D in a moment. I'll tell you what we marked in just a moment. Okay? Okay? Now the next thing we want to talk about is what's called Gibbs phase rule. Gibbs phase rule. Again, this was the same Gibbs like our very first PhD in this country. Kind of an important person. The same guy that Gibbs Free Energy is named after. Gibbs came up with Gibbs phase rule. And what's useful about it is it tells us what things can we change in our system without changing the equilibrium of our phases, right? For example, let's just work through it. So this is the equation for it. It's P plus F equals C plus N. What is P, F, C, and N? Well, P is the number of phases present. F is the number of external variables, or the degrees of freedom that you need to completely define the system. I'll explain what that means in just a moment. C is the number of components in your system, and N is the number of non-compositional variables, right? So let's just walk through these one at a time. Let's do it at point A. At point A, if we were going to apply Gibbs phase rule to try and calculate the degrees of freedom, right? We're going to do P plus F equals C plus N. How many phases are present at point A, our triple point? We've got 3 phases present, right? We don't know what F is. We're going to solve for it. How many components are there in the pure water system? Just one. It's just water. We haven't added salt or sugar or anything else yet, right? So just one. And then what are our number of non-compositional variables? 2. We've got pressure and temperature, right? So in this case, if you solve for F, what does F equal to? 0. So that's the degrees of freedom. We have no degrees of freedom. We can't change anything in this system and stay in equilibrium that we had defined at this point. Because at that point you have solid, liquid, and gas all in equilibrium. And you can't move that point anywhere else. You can't move it, for example, you can't go down in temperature or you get rid of your gas, right? You can't go up in pressure or you get rid of your gas. So there's just one point where this happens at. Now what about point B? What is Gibbs phase rule at point B? Actually do this for points B, C, and D. So turn to a neighbor and let's work on these together. If you've got questions, raise a hand. We got lots of TAs today. Okay, I think this is pretty straightforward. Somebody help me do this. So for point B, how many degrees of freedom do we have? 1. How do we know that? Let's count our phases. We've got 2. We say that we've got 1 degree of freedom. That's got to equal 1 plus 2. Again, that's the only way. We must have 1 degree of freedom. What does that mean? It means we can change one thing, and then if we want to keep equilibrium, the system's going to change everything else. So let's show an example of that. Point B, if I, for example, want to, I'm looking at the boil, that's the melting point, right? So if I go from Salt Lake City to LA, I'm going to go up in pressure. So if I choose to go up in pressure, then the system says, all right, you have to go down in temperature so that you're still on that line. That's the only way that you're going to achieve the boiling point still, right? So you can change one thing, but the system will change the other thing if you're going to maintain equilibrium. Does that make sense? Same thing over here. This is going to be 2 plus 1 equals 1 plus 2. What about point D, though? What's our degrees of freedom at point D? 2 degrees of freedom, right? So again, you've got 1 phase there plus F equals 1 plus 2. So F must be equal to 2 there. What does that mean? It means that we can change 2 things. At point D, we can go down in pressure, we can go up in temperature, and we're still just a gas, right? So we have 2 degrees of freedom. Okay, we'll come back to this. This becomes kind of useful when we get to more complex phase diagrams. Again, this is a single component phase diagram, which is as simple as they get. They get more complicated. Okay, let's move on. So the actual phase diagram for water, by the way, looks like this. This is water. It looks kind of like what I drew. One thing that is really big difference is look at the slope of this line right here. Going from solid to liquid, I drew that really leaning that way. That's a big exaggeration. And actually, water is incredibly unique that it has that. Water is one of not a ton of substances that actually has the slope of the line between solid and liquid as being negative slope. And that is why life exists on this planet, right? It would not exist otherwise. Because imagine, if that wasn't the case, then that means ice wouldn't float on water. That means ice would sink. That would mean that we could potentially have completely frozen lakes and oceans, right? Because it freezes at the surface and then just sink, right? So it's a big deal. It's a very big deal that this exists the way it does. What else stands out to this? Maybe something you haven't realized is that over here in ice, in the blue area, which is ice, there's actually, 11 different types of ice out there. So there are a ton of different ways that water molecules can solidify and actually achieve a solid molecule. There's not just ice. Ice isn't just ice, right? And maybe you've seen this. Skiers, I had a student who was on the Utah Avalanche team a couple years ago in this class, and he's like, yeah, absolutely. Depending on the humidity and the dew point, all these different conditions, your ice, the snow that falls down as ice, right, is completely different. Not only in terms of the crystal structure, but also in terms of the microstructure. In fact, microstructure plays a much bigger role in the type of snow that we ski on, whether it grows in rods or platelets or these the flakes that you see in like the Disney movies. Totally depends on things like pressure and temperature and the moisture level in air. And I think we'll talk more about that a little bit later on. So I just want to show you this. Now, question is, where do we get this from? These are like actual values, right? These are real temperatures and real pressures. So how did we get this? Any thoughts? How would you generate this? How would you do it? So yeah, just like make an experiment where you test these things. That's one way. And they do that. Like people try and dial up, but those are crazy pressures. 100 gigapascals? That's bonkers, right? Some of these temperatures, anyways, how you do that, you can do it experimentally. How else might you do it? Anthony?
You get a couple points of data and then create the best fit data line.
That's exactly what they do. They'll take a couple data points, and then they use our old friend Gibbs Free Energy, and they calculate the Gibbs Free Energy lines for these, and they calibrate it to a few known points, but most of it is calculated, right? So let's keep going. The Gibbs Free Energy calculates these things. So how do we do that? Remember, Gibbs Free Energy is G equals H minus TS. So we're going to teach you today how to plot G versus T or G versus P. So let's put G versus T and G versus P. If we were going to plot it for different phases, how do we do that? Let's do gas in purple. Let's do liquid in blue, and we'll do solid in red. Okay. Well, the first thing we need to do, if we're going to plot G versus T, we'd like to know what the derivative of G is with respect to T so we can plot it. So what is dg dt equal to? We talked about this a few days ago. Again, this is our G expression. If you take the derivative of that with respect to T, what do you end up with? Negative T. Yeah, it's going to be proportional to negative S, not T. It'll be proportional to the negative of your entropy of your system, right? Now what about dg dp? Well, you have to remember, to make this easier, you have to remember that H itself equals U plus PV. So now if you take dg dp, what should it be proportional to? Yeah, volume. So if you're going to sketch these things for these three different phases, we realize that, let's do volume first because it's easier. Which one of these three phases has the largest volume? Gas. Therefore, the slope, since we're doing dg dp, that should have the highest volume. Therefore, it has the highest slope, right? So let's draw it. It looks like that, okay? Now, which one has a higher volume, liquid or solid? For water. Do it for water now. Solid has a higher volume, so let's do the red. So it might look something like that. And then let's finally draw our last one. We need blue. Right? I've drawn these with decreasing slope because we're going down in volume. Now, this is where it really gets interesting. You can then take this and you can look at the points where these things intersect. And how do we know what phase will be present? Oh, sorry, question?
Yeah, so they should have the same starting point?
They don't have to have the same, they don't have to intersect the 0 point, for example, as their y-intercept. Yeah, they don't need to have that. Let me change that blue one, it's bugging me. You redraw that. All right, so it still needs to be a positive slope because it still has a positive volume, right? At any given point in time, how do we know when anything happens in the universe? It lowers its energy. There will be a final exam question on this, I'm sure. Why do we know how anything happens in material science and in the world? Because it lowers its energy. So you guys tell me, if you had the option of being these three different phases at a different pressure, right? If you're right here at this pressure, right? Which one are you going to choose to be? The one with the lowest energy, right? You're going to want to be all the way down here as a gas. So at low pressure, you'd like to be a gas, okay? If you increase in pressure, you're then going to become a solid, and then you're going to become a liquid. And if we look at our phase diagram, we can see where this happens. Where do you go from gas to liquid? Sorry, from gas to solid to liquid? You do so right here. Remember, this line is actually a negative slope. It's just very slight negative slope, right? So right there, as you increase pressure, you started as a gas, you turned into a solid, and then you'd become a liquid, right? This makes sense? What if I wanted you to draw it right here, that transition? So you're at a different temperature, you would have to change it. You'd have to go from vapor, liquid, and then to a solid, right? So the idea behind it is that these lines just represent mathematical expressions for your free energy, which we can calculate, which we will not do in this class, right? But we can sketch them in this class to make them match what we observe in a phase diagram to teach this principle. This makes sense? Let's do it for dg dt real quick. dg dt. This is now going to be the slope of the line. We're just going to draw straight lines again. But the slope of those straight lines is going to be proportional to the negative entropy, right? So there are going to be negative slopes. Which one of these three phases has the highest entropy? Definitely gas. So let's draw it right there. It's going to have a high slope and it's negative. Now then, which one's next, liquid or solid? Liquid definitely has more entropy than solid. All right, so let's draw it like that. And then finally, we're going to draw solid has and it's gone. Where did it go? And it's back. But our lines are gone. All right. Thank you for that, Microsoft. Right? Fair enough? We've drawn straight lines. They have negative slopes, and the highest slope is the one that has the highest entropy. So just like before, we can take lines and see where they intersect. These points at which they intersect, those represent melting points, boiling points, right? These different things we talked about before. So over here, our lowest phase is going to be solid. That's our lowest energy phase. Here, our lowest energy phase is going to be liquid, and here it's going to be gas. So let's take a look at our phase diagram and see where we increase with temperature and go solid, liquid, gas. Where do we go solid, liquid, gas? What temperatures? This is a function of temperature? Yeah, it's a function of temperature.
Basically everything above the triple point, right?
Yeah, so you pick exactly. Above the triple point, any of these pressures up above here, if you take them and run across it that way, you go solid, liquid, gas, right? So that's the approach behind these. This is a very, very simplified approach because we're drawing straight lines and these things don't necessarily have to be straight. But it's a good first order approximation to understand how you go from free energy, which is something we can calculate, to a phase diagram, which is something that we as engineers can use. Okay? On the homework, you'll have the opportunity to draw some of these G versus P and G versus T diagrams for something that isn't water, something like benzene. Benzene, if you froze benzene, it would sink to the bottom. And you're going to have to rearrange that to figure out how that's going to look a little bit differently. Or no, I think that. Anyways, that's a typical problem for this. Let's skip those for now. At the end of class, I'll go ahead and fill these things in so you have them in the notes. But for the sake of time, let's keep going. And let's talk about multi-component systems, right? Multi-component systems. Now we're going to leave the pleasant world where there's just one component, like pure water. And we're going to say, what happens when you take pure water and you add Kool-Aid packet to it, right? Or sugar, or salt, or something else to it, right? How does that change what phases are present? I used to teach this in greater detail. I no longer do, but at the end of this, if you scroll all the way to the bottom of this, you'll see the notes. So if you want to see what, like the full mathematical derivation, it's there. We just don't have time. I don't think it belongs in an intro class anyways. So instead, we're just going to show you some pictures. First off, let's start with sugar and water. If you're like my son and you want your Kool-Aid with like so much sugar and not that much water, right? You reach the point at which you can't just stir the sugar in, right? He's poured like 2 cups of sugar into the pitcher and it's just not stirring in. Why is that? It's just sitting on the bottom. Why? There's a solubility limit, right? There's a solubility limit. So what does it look like for water? Let me pull this up my notes. It looks something like, okay, you've got a positive slope and it's something out over there, right? So if you plot temperature against the weight percent sugar, right? So maybe this is like 100% over here. And this is like 0%. And this is like where most people drink their Kool-Aid. This is where my son wants his, right? There's a point at which there's a line of equilibrium. Over here you have what we call syrup. That's basically what you're drinking, right, when you drink Kool-Aid. And over here you have what? To the right of that line, what do you have? You've got syrup plus sugar, right? And then over here somewhere you've got pure sugar. Right? So here's our very first sort of phase diagram that we can look at. How do we know that that slope is positive? Why didn't I draw it like that, for example? How do you know that it's positive? And it's gone. It's obnoxious. No, we lost some stuff, but it's mostly there. Right? Why is it not the other way? Anybody taken something and tried to increase the solubility? You heat it up, right? This is like Gen Chem first semester stuff. If you want to increase solubility, you stir it and you heat it up, right? You pick things, obviously things that are like dissolves like, but heating it up can make it better. So the solubility, you can put more and more sugar into something and keep it a syrup if you just heat it up. So this is the first introduction of solubility limits that most systems, not all of them, but many of them have solubility limits. There's a limit to how much of your second component you can mix with your first one and keep a single phase. Okay, so that's our solubility limit. Let's talk about copper and nickel now. This is one of the first phase diagrams you usually see. If you start out with pure, let me make sure I get this one right. This is pure copper over here. This is pure nickel over here. The phase diagram looks a little bit like this. Copper melts at a lower temperature than nickel by a little bit. This melts at 1085 Celsius, I think. And this one melts at 1453. I think those are Celsius. They might be Kelvin. But this is temperature on the y-axis. Right? So this would be the weight percent of nickel going from 0% up to 100%. So let's start to label this diagram. What do we have if we take these two metals and we heat them way, way up? What phase will be present? You're going to have a liquid for sure. And if you cool it all the way down, we're going to get rid of the liquids, right? So we're going to call this, let's just call it a Greek letter alpha. We could have chosen any letter, right? But that just represents that it's a single solid phase because these two elements are so similar to one another that we have what's called complete solid solution. This thing, the fact that we can go all the way across there and it's a single phase, that represents complete solid solution. And it's because they're so similar. Yeah, complete solid solution. Just like you can make a solution of liquids, right? Sugar and water, it's a solution. You can make a solid solution, which is something kind of interesting to think about, right? These are atoms, but they're just perfectly mixed together. Now, what about this middle region? What do we have in the middle region? Yeah, the way that you always do this, anytime that you're labeling a phase diagram, to figure out what's in a region, you just look at what's on the left and what's on the right at a constant temperature. So at this temperature, on the left we have liquid, on the right we have alpha solid. So in the middle we must have a mixture of liquid and our solid, right? Any questions so far on this?
Does it matter if it's alpha plus? Is it
Nope.
whatever's the most?
Yeah, you can write L plus alpha or alpha plus L, same difference. It's just saying what phases are present. A more important question are these two things. First off, what's the composition of the liquid and the alpha? That's our first question. And the second one is, how much of them are there, right? So at this temperature, let's call this T1, we'd like to know, first off, what's the composition of the liquid and the solid present there, and how much of them are there? So anybody from the reading want to take a stab at this? How do we know what's what? In the red shirt, I can't see your face.
The lever rule, where you go to the side.
Yeah, what does the lever rule tell us?
The composition.
That will tell you, well, it'll tell you both. First, it's mostly used to tell you how much, the amount. How do we figure out the composition again? Somebody remember this? You drop, yeah.
You draw the vertical lines down to...
Exactly. So we're going to draw vertical lines down from where it intersects these phase boundaries, right? These represent our phase boundaries. So we can drop this down and drop this one down. This right here is going to represent the composition of our alpha phase, whereas this one here will be the composition of our liquid. So what does this tell us? If you go up or down in temperature a little bit and let this thing reach equilibrium, remember all phase diagrams are assuming equilibrium, but you don't always reach, right? So phase diagrams are really imperfect in that way. They assume equilibrium. Sometimes that might take a long time. But if you go up in temperature, what do you do to your composition of your solid liquid? That's bizarre. I'm going to have to... It does not. And now it's real mad. I don't think we want to delete anything. Still there.
What are you using to capture?
I use flashback. So if you go to a different temperature, let's draw a different temperature and hope it doesn't freeze again. Right, let's go up in temperature. We have two different composition values for our liquid and our alpha, right? This makes sense? So at any given temperature, I could say, at this temperature, tell me the composition of the liquid, right? Or tell me the composition of solid. And you just have to identify, draw a flat line, see where it intersects those two, what we call the solidus and the liquidus lines. Let's label these. This here is called the solidus, S-O-L-I-D-U-S. solidus, and this one up here is called, this is just a really good punk that someone's doing on me. The solidus and liquidus lines, I might have to restart this in a minute.
Is that like a button you're accidentally?
Maybe, I don't think so. Solidus and liquidus, right? So you've got your solidus and you've got your liquidus lines. Okay? Any questions on this so far? Again, this is a simple phase diagram because these two elements are so similar to one another that they can be completely dissolved one into another. Okay? So just because they can dissolve into one another, that doesn't mean that copper and nickel are the same, right? Clearly they have different melting points for one, right? We can see that on this phase diagram. They have different mechanical properties. They have lots of different properties, right? But what it does mean is that they must have the same crystal structure. Again, crystal structure is the way that atoms arrange themselves. If you imagine in a really simplified scenario that you have like copper is like your atoms arranged like this in some sort of square, that they make sort of like this repeat square that you could tile and fill space with. You could just place atoms, right? We can introduce a new parameter called the lattice parameter, A. Lattice parameter. The lattice parameter is basically, it has to do with the separation when you repeat these things over and over. And if you go from pure copper to pure nickel, even though they're the same crystal structure, meaning that they're both a square arrangement, that doesn't mean that they have to have the same lattice parameter, right? So for example, nickel could be much larger. It could have a much larger lattice parameter. I don't remember which one is which in real life, but that's the idea. Like you could just vary it, okay? And as you go from pure copper and you slowly start to toss in nickel atoms, your lattice slowly gets bigger and bigger and bigger and bigger until by the time you get to nickel, it's that big. Therefore, we can plot something called Vegards' law. Vegards' law is this. As you plot a lattice parameter, against your weight fraction of going, from pure A to pure B component, you should see data points that look like this. It should be linear, and if it stops being linear and then it stays constant, what do you think that suggests? Maybe turn to a neighbor. What does that suggest? If you could somehow measure this lattice parameter for all these different compositions, and it's increasing nice and linear, but then it stops, what does that suggest? Talk to a neighbor. Okay, what do we think? Who's never made a comment in this class before? Okay, he's pointing. He's calling you out, bud. What might that represent?
I think it represents as solubility.
That's exactly what that represents. You've reached your solubility limit, right? Solubility says you can take one of these atoms out, put another one in, and it doesn't change the crystal structure. So if this continues to increase, then you must be switching atoms in and out and slowly changing the size of the structure, but not the type. But all of a sudden, when it stops increasing, that means that you've hit your solubility limit. So one way to determine phase diagrams, you know that this must be your solubility limit. One way to do this is to make a bunch of these different alloys at a bunch of different temperatures, check their lattice parameter with a tool that we'll learn in 2 chapters, and then look what these things look like, and then you could recreate a phase diagram, right? That's kind of a pain in the butt way to do it, but you could do that, okay? So let's keep going. Let's introduce a new type of phase diagram, the next most challenging one. We've done a simple one, and we'll probably end on this one today. Is as following. It's called the binary eutectic phase diagram. So again, we're going to go from pure A to pure B. There's pure A, there's pure B, This is temperature. That's almost always what these are plotted against. You can do it against pressure, but that's not common, right? And we're going to show what happens here. If it's a binary eutectic, then that means we have to have a eutectic reaction. A eutectic reaction is one that goes from a liquid reversibly between two different solids, say alpha and beta. Meaning that there is a eutectic point, means that there's a certain point on this diagram where if you cool down or heat up, you'll undergo that reaction. One liquid of a single composition switches to two different solids of different compositions. Okay, so let's draw what it looks like. It might look something like, let's switch colors. You've got something like this. Okay, so let's start labeling the different regions on here. Like usual, the very top of the phase diagram, that's when you've heated things up a ton. That's where you're going to have your liquid phase. Or, if you kept on heating it, I guess it'd be gas. They don't ever show it on these diagrams. But this is going to be your liquid up here. Now, where else can we start to label? The very bottom, that's where we're going to have what? Alpha plus beta are two phases here. And again, anytime that you have a region, the things to the left and the right tell you what's in here. So we can call this one alpha and this one beta. You can call it vice versa if you want. Just convention is to do alpha on the left and beta on the right. And then again, these regions right here, if you want to label it, you're just going to look what's on the left and what's on the right. So what about this one on the left? How do we label it? Yeah, alpha plus liquid. And then the one on the right is beta plus liquid. Okay? Now, where is our eutectic point? At the bottom of this thing, where it comes to the bottom of that V, is our eutectic point. Right there, that should be touching, right? That is our eutectic point. So the eutectic point has to have a specific composition, right? We call this the composition sub E, composition of the eutectic. And we call this temperature that it happens at the temperature of the eutectic, or the eutectic temperature. Okay, any questions so far? So what this is a key point, because if you have a liquid that's just above that temperature, a few degrees above it, and you start to cool down below that line, what that means is that all of your liquid, without slowly converting, it's all going to transform into a solid, right? Whereas imagine this scenario, if you have a different, let me switch colors one more time. If you cool down right here, that's not what's going to happen. For example, as you're cooling down, you're going down in temperature. As soon as you touch that line, what happens? The very first alpha begins to precipitate, right? If this is in like a crucible or a beaker, and you start to cool it down, your very first solid is going to form. Where's it going to form? Where do solids form when you cool them down in liquids? It can happen anywhere. Where does it tend to happen? Anybody seen like a water bottle freeze? Happens on the edges, right? We'll talk about why that is when we get later in this chapter on kinetics, but it tends to start from the edges. So you have little tiny grains, we call them, grains of solid forming. What's the composition of that alpha phase that's forming? Anytime I ask what the composition is, all you have to do is draw a little line over, and you say, it's right there. It's whatever this is, 5 or 10%, right? You could look up what the value is there, right? So as you continue to cool this thing down, what happens as you cool down through that region? More and more solid forms at the expense of your liquid. So your liquid is going away as more and more solid forms. And at the point just above this line, right there, just above our eutectic reaction, do we have any liquid left? Yes. By raise of hands, who thinks yes? Who thinks no? So which one is it? That's pretty even split. A lot of people didn't vote, right? So first off, because it's above that line, we're in the alpha plus L region. We must have alpha plus L there. We haven't learned yet the lever rule, which tells us how much, but we know that there still must be liquid there. And as soon as we cross below this line into here, this says alpha plus beta. Therefore, any liquid that we had must have converted to a mixture of alpha and beta. That's because when you go across this line right here, that is the eutectic reaction. Any liquid that's left over, be it a little bit or a lot, right? At the eutectic point, it's all liquid, and it all simultaneously converts. And near these edges, it's actually not very much liquid left. But as soon as you cross that purple line there, any liquid you have left undergoes the eutectic reaction. You get two solids. We'll answer a couple questions. We'll wrap up. Yeah, question?
What does beta represent?
Beta represents, for the sake of this class right now, it's just a different type of crystal structure, right? If alpha was like a square arrangement, this could be like a hexagonal arrangement. One other question I saw? Okay, we'll pick up here next time.